All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207, Calculus 2. Let me share the screen with you guys. We are going to jump right in. Okay, so I think that looks good. So maybe a quick recap is in order. So last time we did, we learned a new technique called trig substitution. And this is basically when we substitute a trig function in hopes that our integral becomes easier. So one basic example here is this one, the integral of x squared over the square root of 4 minus x squared dx. It turns out a regular substitution here would not have worked. It's not a basic rule. You can't really simplify it to get a basic rule. However, the expression in the denominator, 4 minus x squared, is in the form a squared minus x squared, where a is a constant. And so we have the option of using something called a trig substitution. That option is based on this table right here. So basically, if I have an expression that looks like a squared minus x squared, or a squared plus x squared, or x squared minus a squared, expressions of that sort, I am allowed to use something called a trig substitution. And these guys are very general. Your a doesn't have to be a whole number, and your x squared, technically speaking, doesn't have to be an x squared if you can get a nicer substitution to work. But it has to look like sort of a difference of squares or a sum of squares, or in that order. Anyway, so now we have some more people trickling in. Okay. All right. So once you have one of those forms, you have the option of using a trig sub, and this is something we'll talk about later on. You don't have to use a trig sub, but it is an option. And it might be the best option to choose, it might not be, and we'll talk about that a little bit later. But in this case, the optimal solution was x equals 2 sine theta. You plug this in. Now, once you do that, once you apply a trig sub, you have to notice that you don't have trig functions in the beginning. After the substitution, now you have a trig integral. And the last section taught us how to deal with trig integrals. So in theory, once you actually do a trig sub, you end up with an integral. You will be able to do that integral based on what we were doing in the last section. And voila, you will normally get an answer in another variable, in the variable of the angle, for example, so in the variable theta. And to change it back to the original variable, if you have to do that, you would actually use the original trig substitution to figure out what right triangle that applies to. Using Pythagoras' theorem, you can actually find all the other side lengths and hence find all the other trig ratios. Then you can just substitute that into the theta version of the answer to get back the original x version of the answer. Okay, so that is a process that we call back substitution. And as you can see here, it's actually tedious. It's a whole other page of work after us doing a whole other page of work. And therefore, the recommendation is whenever you have a definite integral with trig sub, you kind of want to change the limits so that you don't have to do the back substitution part. And we'll see some examples of that later on. Okay, we did a couple more examples and I had you guys try these for next time. So here is where we are. So we start here on, I believe today is the 21st. Okay. And so at this point, I would like to see what you guys were able to come up with. So let's actually do that. Let me move this out the way here. And so we can actually begin. So move this guy down. All right. So go. Tell me what you guys could do with this one here.
My first step was to complete the square, so I got everything under the square root to be x plus 2 quantity squared plus 4.
Oh, did you purposely turn off your mic, or did something go wrong?
Yeah, that was just my first step.
Okay, yes.
So did you get it
So
all?
complete the square. Remember how complete the square works. You would put x plus 1/2 of the coefficient of the linear term inside there. and you all squared it. Of course, when you square the constant term, you get a +4. In order to get back to the original of +8, you would need another +4. And so that is what the complete square would look like. So first step here was complete the square. Why did you decide to complete the square?
Because it wouldn't factor nicely and I wanted to get it into the x squared plus a squared format.
Right. To get the x squared plus a squared form. So remember, in our trig substitution, there are 3 forms that we can apply them to: x squared plus a squared, x squared minus a squared minus x squared. So you have a difference or a sum of squares. And so completing the square is actually a good idea. Whenever you have a quadratic all splayed out, completing the square allows you to get it into one of those forms. So yeah, that was the first step. Now what?
I chose a to be 2, and then I substituted 2 tan theta in for x plus 2.
Okay, so the 4 here, that's 2 squared. So this means that your a equals 2. And so this guy here, that's like your x from the table. So that's your variable. So then you do the substitution. Let x plus 2 equals 2 tan theta. Why do you do 2 tan theta? Well, if you look above in our table, which you really should have this whole table here memorized, in the second row, you would see that whenever you have a squared plus x squared, x equals a tangent theta is going to be the optimal solution to use. Okay, once you do that, what do you do?
I squared it, and so I had 4 tan squared theta plus 4. Then I factored out of 4 and replaced that tan squared theta plus 2, or plus 1, sorry, with a, I like took the square root of the whole thing.
Squared it.
Yeah.
So x plus 2 squared is equal to 4 tan squared theta. And what did you do with that?
And then I had 4 tan squared theta plus 4, so I factored out of 4 and then replaced the tan squared theta plus 1 with secant squared theta, and then took the square root of it to get 2 secant theta.
Okay, so you did that part here where you plus 4. Let's get 4 tan squared theta plus 4. And so that's just 4 secant squared theta. And so that means when you took the square root, you have 2 secant theta. So that's the new denominator.
Professor, can I jump in with a question?
Yep.
So I'm not really sure how you get x plus 2 to be 2 tan theta, because like I know in the rule it's supposed to be x squared plus 2 squared.
Yes, but this is what I was mentioning earlier. The x, you just want to think of it as a stand-in for a function. So basically, it's whenever you have a variable squared plus a squared, you can substitute the variable equals a tan theta. So you want to think more general. So here your variable is actually x plus 2 as opposed to x.
Right, but that would be like x squared plus a squared equals a tan theta. But I'm saying you don't have an x squared, you only have an x.
What do you mean you only have an x?
Like the rule says x squared plus a squared equals a tan theta, right?
Well, you would
Well,
set x equals a
equals-
tan theta, yes.
Right. But here you only have x plus 2.
Okay.
So there's no x squared plus x plus a squared to get you to get a tan theta.
Yeah, but what I'm saying is the x plus 2 is like the x in the table,
Okay.
right? You know how like
Oh, so is it like 4 is the a in that one?
yes, 4 is the
Okay.
a squared.
Okay, okay, okay. Sorry, thank
And the
you.
x plus 2 is like the variable.
Yeah, okay.
You know, it's kind of an algebraic thing. So you remember, like, if I told you, or let's say you knew x squared plus 2x plus 1, right? Someone told you that you could factor that as x plus 1 all squared, right?
Right.
And then someone else says, oh, what if you have x plus 2 squared plus 2 times x plus 2 plus 1? Nothing really changes, right? The same rule applies. It's just that instead of x, you now have an x plus 2. The same idea holds. You're going to put that thing plus 1
Right. Squared.
all squared. The
Mhm.
strategy doesn't change just because
Okay.
your variable has a different form,
Okay.
right?
I
So
didn't.
it's like here, instead of an x in your table, you have an x plus 2.
Right.
Doesn't matter. It's something that's changing. It's a variable and it's squared.
Yeah. Okay.
So you have something that's changing and it's squared plus a constant that's squared. So you have that option to do that substitution.
Okay. I thought you were just saying that like the x plus 2 was the x squared plus a squared, but I was like, that's not x squared.
Oh
But
yeah,
I
no.
understand. Yeah.
The
Okay.
in what I'm saying here is that, let me do it. What I'm saying here is the x plus 2 is like the x,
Yeah. Okay.
and then the 4 is like the a squared.
Thank
So
you.
this is like the x squared plus the a squared here.
Gotcha. Thank you so much.
Yeah. All right. So yeah. So now the next step would be to actually do the derivatives, because we need to find the dx and d to replace the d theta. So you differentiate both sides. Derivative of tangent.
Secant squared.
So that's secant squared theta d theta. And so now you go and you plug these guys back in. So we already worked out the denominator here. So that's actually just going to be 2 secant theta. That was what we worked out here. And then the dx now becomes 2 secant squared theta d theta. So now this guy, we'd be able to simplify. So the 2's cancel. The secant cancels one of those. And so we end up with just basically the integral of secant theta. Right? Is that what you got?
Yes.
Okay. So, I don't know. This is kind of really close here. Can I move this? Okay, so now we're at secant theta. How do we integrate secant theta?
ln times absolute, or ln of the absolute value of secant theta plus tan theta plus c.
Yes. So this is ln of secant theta plus tan theta plus c. And that's actually the integral. That's your answer in theta. How do we go back to x's? You do something called back substitute. How does that work here?
Since we know that x plus 2 equals 2 tan theta, I found that tan theta equals x plus 2 over 2. And so I plugged that in for the tan theta part, but then for the rest, I drew a triangle where my hypotenuse is square root of x squared plus 4x plus 8. And then the adjacent angle is 2, and the opposite angle is x plus 2.
Right, because tangent is opposite over adjacent from SOHCAHTOA. So you know that the opposite is x plus 2, the adjacent is 2. The hypotenuse is going to be the sum of the squares of these. So you're actually going to get x plus 2 squared plus 4, and then you take the square root. And so from that, what did you use that triangle to figure out?
I used it to figure out secant theta, and for that I got square root of x squared plus 4x plus 8 all over 2.
Right. So this means that your secant can be, well, it's hypotenuse over adjacent. So that is going to be x plus 2 squared plus 4 all over 2. So now you know what the secant is. And you know what the tangent is. And those guys apply to maybe. Those guys apply here and here. So now you would have ln of the secant plus the tangent. And that's your answer. Now, here's something I want you to note. If you were to do this problem in a typical calculus textbook and you were to arrive at this answer, and then you want to check your work, so you flip to the back of the textbook to check your answer, chances are the answer would not be written in this form. Chances are in a text, the answer would likely be written as ln if you look at the back of the textbook, you'd see something like that, right? So at this point, you might be worried that, did I do something wrong? Is this the wrong answer? Are these the same? Are these answers equivalent? Like, is this correct? Like, what happened here?
You'd have to expand it using the logarithm rules, and then part of it would like become the new c constant. So technically it is equivalent, I think.
So why is this okay? Well, if you start with ln of the square root of x plus 2 all squared plus 4 all over 2 plus x plus 2 all over 2. Yeah, what are you saying now?
I was saying combine those, so you have square root of x plus 2 quantity squared plus 4 plus x plus 2 all over 2, and then use logarithm rules to do like ln of the numerator minus ln of the denominator, but ln of the denominator, sorry, just like gets replaced by c.
So you get a new plus c, which is just the sum of those constants. So one thing you have to be careful of with integration is it's possible to get an answer that looks radically different, no pun intended, than what you might have worked out initially. And this is because, well, there was this part in Calc 1 where you learned about what an antiderivative is, and you learned that it was not unique. There is no unique representation of an antiderivative, because at the very least, every antiderivative you can think of, if you can add a constant to it, it is also an antiderivative. So antiderivatives aren't unique. And this doesn't just boil down to just adding constants. You can actually have antiderivatives in completely different forms, speaking variable-wise. And what all antiderivatives will have in common is that they will differ by a constant. So that's something that you have to keep your eyes out for. So sometimes you might be working on a problem and you might get an answer and you look up the answer and it looks like completely different from the answer that you got. It doesn't necessarily mean that you got something wrong. You have to actually check, can I simplify my answer to get that answer that I'm seeing? Or is my answer different from that answer by just a constant? Because all of those can be issues. And so it's a very common issue at this point for students to start to discover that, and they think they're doing something wrong, and they might try a problem 100 different times, 100 different ways. And like, I keep getting the same answer, and I don't know what I'm doing wrong. And it's like, you're not doing anything wrong. It's just that if you simplified your answer or just do a little bit of computation, you'll realize that you can get the answer to look completely different. So this is just something that I wanted to point out at this point. Sometimes it's easier to typeface, it's easier to type the second answer that I put in the red box than it is to type the first answer that we got in the white box. And so just for like conciseness or just for ease of typing, your textbook just might decide to put the answer in a certain form. Just be aware that your antiderivatives can have a different form. It doesn't necessarily mean that you got the wrong answer. You just have the wrong form of the antiderivative. And there's nothing strange about that. We know that antiderivatives aren't unique. It's not like derivatives where you'd pretty much always get the same answer. You can algebraically simplify, but that's pretty much it. For integrals, it's a little bit more complicated than that. Of course, not surprising, right? Integrals are more complicated than derivatives. Okay, so I just wanted to take the opportunity to point that out because I think that's actually a very common issue. Okay, that being said, we've been spending a lot of time. Let's actually speed up here. So I went really slow through that example just to make sure that everyone's back up to speed. Last time we spoke about all this was last week. So, all right, let's move a little quicker on this. Another input.
Okay, so for this one, first I like to write it as like 1 over times dx just because it makes it easier for me.
Okay.
And then I know that this is a little weird, but I actually decided to factor out a 4 and then do like 4 times x squared plus 1/4.
Okay.
Because because I didn't really, like for the other one, I was a little confused, like how to get like.
Yeah.
So like
I mean, it's not wrong. I mean, you could go and factor out the 1/4 and you would end up with something that looks like this.
Yeah, and then so that was 1/2 tan theta equals x. And then
Yeah.
I drew the triangle, so it would be the opposite of theta.
Yeah, and you'll actually get the equivalent thing. You'll notice here that if I were to do probably the nicer way for you to think about it, there's a time when you might do what I wrote in blue here, but a nicer way to think about it was just to think of the 4x squared
Professor, I'm so
as
sorry.
2x all squared.
I'm so sorry. I'll be right back. Sorry.
And then let 2x, okay, equals the tan theta. You'll notice that it's the same. But yeah, of course, once you actually do that, you can do the derivatives. So then you realize that your dx is equal to 1/2 secant squared theta d theta. You go into the original integral and you plug that in. Let's call this I. So now you have here your undo. You have here your 2x all squared plus 1. If you were to actually plug in for the 2x a tangent, you would look like tangent squared plus 1. So it just actually becomes secant squared. Undo. So the denominator of your integral becomes the square root of secant squared. Your dx would be 1/2 secant squared theta d theta. And again, this would actually simplify to 1/2 times secant theta. Integrate that. And so now you want to do that back substitution. You know that your 2x was equal to tan theta. So this means that you can get this triangle where you think of this as 2x over 1. And so the opposite is 2x. The adjacent is 1. And of course, you get 4x squared plus 1 square rooted up here. And so this means that your secant is going to be hypotenuse over adjacent. And so now you can plug that in. So this is 1/2 ln of secant plus tangent. And we have that. Agreed?
Yeah.
Okay, awesome.
Yeah, I have that.
Okay, someone tell me what answer they got for this one.
X over square root of x squared plus 1 plus c.
That's the answer you got? Okay.
Yeah.
What substitution did you do?
I took x to equal tan theta and dx to be secant squared theta.
So if you put a tan theta where the x is, you get tan squared plus 1, which just gives you secant squared. And your dx would become secant squared theta d theta. What you would have here is that the over 2 cancels the square here. And so you just have secant squared over secant cubed. Okay, how do you integrate that?
Isn't that the same as 1 over c,
It's 1 over secant, and so?
which is the same as cosine? So the integral of that would be sine theta plus c.
Okay, how do I know what sine theta is in terms of x's?
I drew the triangle and so my hypotenuse is square root of x squared plus 1. My opposite angle is x, and my adjacent is 1. As then, since sine is opposite over hypotenuse, that's where I got the x over square root of x squared plus 1.
Okay, so this means that your sine is opposite over hypotenuse. And so that's x over the radical of x squared plus 1. And so this means your I is just equal to that guy. Yeah, so that was correct. Let's keep going. We're on a roll. All right. Boom, 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 boom. Another example. All right, go.
So what I did for this one, I said that the numerator would be like the x squared minus a squared.
Yeah.
And then, so I have x equals radical 3 secant theta.
Yeah.
And then when I did it in
Your
the,
dx is going to be secant theta tangent theta.
yeah.
Okay.
And then, so because it was, so this is going to sound weird, but I drew the triangle and I realized that radical x squared minus 3 over x is actually sine theta when you draw it in the triangle.
Radical x squared over 3?
No. So, so like when I drew the triangle and that's secant theta, so then radical 3 would be the adjacent, and then x would be the hypotenuse.
Yeah.
And then the opposite side I thought was radical x squared minus 3.
So you drew the triangle and you said secant
I have those
is,
switched. I'm sorry. I have those switched.
yeah, hypotenuse
Yeah.
over adjacent.
hmm
And so this is that. Okay.
So if you look at the triangle x, this x squared minus 3 radical over x would actually just be sine theta.
Okay.
So then I just had sine theta dx, or d theta, sorry.
Okay. And it might eventually simplify to there. I mean, so from here, you can get that sine theta is equal to,
It was just something I noticed, so I just,
okay.
yeah.
Yeah. Interesting. That's cool. I mean, that'll work out. We'll eventually get there. I'm not sure that's something that you can do in general, but yeah, that looks fine to me here. But if we wanted to go more traditionally, what would we do here? Maybe someone else can tell me how they would continue.
I substituted square root 3 secant theta for x, sorry. So my new equation was integral of square root of 3 secant squared theta minus 3 over root 3 secant theta times root 3 secant theta tan theta d theta. It's a lot of thetas.
Okay, and then what? So the top would be what? Radical 3 tangent? Right? Because it's the secant squared minus 1 after you factor out the 3.
Yeah.
And so that's just gives you tangent squared. You take the radical of both, you get that. And if we simplify, so this cancels that, this cancels that. You would get radical 3 tan squared.
Yeah, and then I used the Pythagorean identity to change that to secant squared theta minus 1.
So the integral of secant squared is tangent. Okay. All right. And so what do we do now? So what were the limits? 2 and radical 3.
Yes, but then I went back and plugged those into my original like x equals root 3 secant theta equation.
Right. So normally, that's what you should have done first. Like if you think of like the order in which you want to do things, that's probably something that should have happened earlier. So what I would do here is change the limits. And I would go further to give the following recommendation. Always change the limits if doing a definite integral via trig sub. In almost every other case, it's kind of optional. You change the limits if you want to, if you feel like it, if it's just your thing. Yeah, when it comes to trig substitution, always change the limits. It's actually going to save you a lot of work. So that being said, tell me how you actually did that.
Okay, well, I rearranged it so I had x over square root 3 equals secant theta, but then to make it easier for myself, I flipped it so I got root 3 over x equals cosine theta, and then I did inverse cosine of root 3 over x equals theta, and then I plugged in both 2 and root 3 for x.
Okay, so now you can just change the limits. When your x equals 2, let's say, this means you have cosine theta is equal to radical 3 over 2, which means that your theta would be cosine of what is radical 3 over 2?
5 over 6.
And then when x equals radical 3 was the other one. So this means that cosine theta equals 1, which means your theta equals 0. And so these become the new limits, right? So you would put 0 up to pi over 6.
Can you explain like why you did that again? I don't really understand.
Come again?
Can you just like explain why you changed the limits again? Like I don't understand, like I'm not following.
Okay, so here you notice that the original problem was given in terms of x, right? So here, notice the x limits are radical 3 to 2, which means when you see radical 3 to 2, these guys here are x values, right?
Yeah, that makes sense.
Because they're numbers on the x-axis, right? So now here, when we change our integral to thetas, those numbers on the x-axis don't apply anymore, right? Because they're on the x-axis. Now we're integrating on the theta axis. Now, oftentimes when it comes to integration, you could leave it. So let's say I had the integral from 0 to 1 of, I don't know, x squared plus 1 to the 5th, x times x squared plus 1 to the 5th. So now in general, you have two options. One, you can leave the old limits. In which case, what you do here is you'd say u equals x squared plus 1, your du is equal to 2x dx, your 1/2 du is going to be that x dx, and so you can actually just plug that in. So this is going to be 1/2 u to the 5th du, and so what you would write on your limits, you would say x equals 0 to 1. And so then you can integrate that. And then you would just back substitute. You know that your u, is actually x squared plus 1. Why did I put over 3? And so now you can plug in the old limit. So you plug in a 1 and you get 1/2 times 2 to the 6 over 6 minus you plug in a 0, you get 1/2 times 1 over 6, right? And that would be your answer. Or you have the option to change the limits, right? So what that means is after you do this substitution, u equals x squared plus 1, your du is equal to 2x dx. You have your 1/2 du is equal to x dx. And what you can do is now when you go plug it in, you can also say when your x equals 0, this means that your u would equal to 1, right? Because you just use this line up here. Use your original substitution equation to solve in terms of the other variable. And then you can say when x equals 1, you get that your u equals 2. And so now when you go back to that integral, you would actually get the integral from 1 up to 2 of u to the 5th. Now when you integrate, you can just directly plug in 2 and then plug in the 1, right? So you get the same answer anyway, right? Right? So this is something you would have done when you did substitution in Calc 1. You would have saw that you had options. You could actually leave the limits and not change anything. Just know that before you plug in those numbers, you have to remember what variable you applied the numbers to, which is why it'd be good for you to actually write down x equals blah, so that you remind yourself, oh, it's x equals, x equals, x equals, x equals, x equals, right? So you don't actually plug these numbers into the u because they're not u numbers. But then once you plugged in back the x variable, you now can plug in those old numbers into the x variable, right? So that's always something that you can do. Another option was you could just change the limits. Now what that does is we don't need to put back the old variable to plug in the numbers. We already changed them to the new variable. Right? So that's the difference between these two methods, right? Now, when you notice that, here's the thing. When you're doing every other thing, like when you were back in Calc 1 and you were doing substitution, it wasn't that big a deal. As you can see, these two solutions, they aren't very different. So at one point, your Calc 1 professor probably told you, it's option. You can do whatever you prefer. It's preferable, or, you know, it doesn't really matter, right? However, what you would have seen in trig substitution is that it actually switching back to the old variable is actually a whole other process that you have to go through. So when it comes to trig substitution, this line right here, to go from this line to the answer, it's actually a lot.
Professor?
To switch from this line to that line is actually a bigger deal in trig substitution than it is in a regular substitution. So what I'm trying to say here is that when we're doing trig substitution, I would recommend that you always change the limits, because now you don't have to do that whole triangle thing anymore. Yeah.
I was just wondering, so like when you in that example that you change it from the u substitution, like technically you wouldn't, that obviously there's no back substitution in that, but if it was like one with like cos theta and tan theta, there would be no back substitution for the definite integral, and that would make it easier.
Well, technically speaking, your back substitution happened here.
Right. Okay.
It's just that for regular substitution, your back substitution is trivial. It's like not a big deal. You're right. You literally just look at the equation and you plug in
Right.
where the u's were. For trig substitution, it's a bigger deal, right? You have to draw that triangle and figure out, okay, this is the trig function I want, use SOHCAHTOA, and then you come back and then you plug it in, right?
Right.
So this is the back substitution phase for a regular substitution is just not a big deal. However, in the trig substitution, it is a big deal. And so if I can find a way to skip that whole part, it actually has a lot of benefit. So when it comes to a definite integral, there is a way you can skip that whole part. And that way is to literally just change the limits in the first place.
Thank you.
So should I leave this here? With trig sub, this is a big deal. and requires more calculation in general. Why change limits for trig sub? Yeah, so normally because always is a very strong word. And when it comes to mathematics, you really have to justify why would you say always? It's very rarely the case that something is always true and in every scenario, it would be the way to go. But this is one of the scenarios I would actually consider it like always change the limits when you're doing a trig sub and you're doing a definite integral. It's like 99% of the time, it's gonna save you a lot of work. So yeah, I would always change the limits here. That being said, now what you're going to realize is that when I change those limits to 0 and pi over 6, so now this is 0 pi over 6. 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 Now, these guys are theta. We can plug these directly into theta. There's no need to change back to x's. There's no need to draw that triangle and figure out SOHCAHTOA and then convert everything. And what is the tangent of theta? What is the theta? Oh, the theta I can think of as, what was our original substitution? A secant inverse of x over radical 3. Like there's no need to actually worry about that. So here we can literally just actually plug in these new numbers now. So this is just going to be tangent of pi over 6 minus pi over 6 minus tangent of 0 minus 0. What's tangent of 0?
0.
Tangent of 0 is 0. So, and of course 0 is 0. What's tangent of pi over 6?
Radical 3 over 3.
Radical 3. Oh, you rationalized. Okay, yes. Radical 3 over 3. I would have just did 1 over radical 3, right? Because it's in that column. Okay, that's going too much in pre-calc. Let's never mind about that. Okay, so this now, of course, is pi over 6. And so finally, our answer looks like radical 3 times radical 3 over 3 minus pi over 6. So here, no need to change back to x's.
Could we also distribute the radical 3 and it would be like correct?
Yeah, it'll be the same thing.
Okay.
So that is why I would always change the limits. Let's start here. This over. I wasn't sure if I was going to keep these notes, so. Let's actually keep them. Okay. So that was another big example. Where are we? Okay, this one. What did we do here?
So here I completed the square again.
Completed the square. Okay, so in order to complete the square, what do you need?
I factored out a negative and
Right,
then,
because you need the coefficient of x squared to be a positive 1.
and then I did
And-
plus 4 minus 4.
Right, so now you complete the square on the inside. So it's going to be x plus 2 all squared. That's going to give you a plus 4, so you subtract 4 to get back the original. And this is all under a radical. And so now you end up with, it ends up being the square root, and underneath you have 4 minus x plus 2 all squared. Okay, so you complete the square again.
Do you have to complete the square again?
No, complete the square again, as in like we did in a previous example.
Okay,
Not-
gotcha.
Like we're not going to complete the square again here. Like this is good. Like once we do this, now what?
Here I just recognized that this would be sine inverse theta of x plus 2 over 2.
Right. So x plus 2 is a sine theta. So my dx is going to be. Oh, what you said was like there's a formula for it.
Yeah, I just figured that was the easier route, and so I did that.
That is the easier route. I'm not sure everyone would see it. So let me actually do the longer route, and then I'll actually make a note of that. It's good that you saw that, but I'm not sure if most people would have noticed that. Yeah, there is a formula that you would have memorized in your basic rules where it's like 1 over the radical of 1 minus x squared equals sine inverse of x plus c. You have to tweak this one a little bit to get it to look like that, but you can do that with, however, it will be x plus 2 all over 2. Let's continue with this though. This will be cosine. So now when you go and plug this in the denominator, you have 4 minus 4 sine squared theta. That is 4 cosine squared. Then you take the radical. So that's going to be 2 cosine theta in the denominator. Then you multiply by 2 cosine theta d theta. And so this is just the integral of 1 d theta, which we know is theta, which you should know is sine inverse. Right? Just by looking here, you know your theta is sine inverse of x plus 2 over 2. So here's something that your suggestion, you could notice something else. Recall, that's supposed to be a colon. Recall the integral of 1 over the radical of 1 minus x squared dx is equal to the sine inverse. So if you have the radical of 1 over the square root of 4 minus x plus 2 squared dx, you can think of this as, you can factor out the quarter. You can factor out the 4. When it comes outside, it's going to be a half. And on the inside, you'd have 1 minus x plus 2 all over 2 squared dx. And so this is going to end up being 1/2 times 2 sine inverse of x plus 2 over 2 plus c. And you can get to that with a quick u sub. So you'd get sine inverse of u, and then that brings you back here. So yeah, if you notice the formula, you could actually do this integral in your head a little bit by just factoring out the 4 so that you get that form for the basic rule. So this was actually something that you could simplify to look like a basic rule and get a substitution to work. If you didn't see that though, a trig substitution wasn't too much trouble here, but yeah, that was another way to do it. Let's see. This is one of those question marks. Okay, how do we do this one? What's the trig sub?
So I did, like, so it's a squared minus x squared, so that would be sine theta. So then x equals 2 sine theta. Right.
And then what would you do here?
So I don't know if this is right, but I actually drew the triangle. And then I tried to see like what cosine was based on the triangle.
So sine is opposite over hypotenuse, so this would be that.
Mm-hmm. So then I have the answer is radical 4 minus x squared over 2 plus c.
Isn't there like a -2 left over?
Oh, oh, I actually had that here, and then I didn't realize what I did. Yeah, so then, yeah, that's what I have.
Okay,
I have a question about that one.
yes.
Could we have just done a clever u squared is 4 minus x squared and not done the trig substitution?
Yeah, I did that, but with u equals negative x squared plus 4. And it was
Exactly.
like easy, like 3 steps.
Better. There's a much better way to attack this one. A regular u substitution would have worked, right? So if we did like a u squared is equal to 4 minus x squared, your 2u du would equal to minus 2x dx. And so you would get minus, this will be u, and this will be u. And so you just have to integrate 1 du. And so this is minus u plus c, and your u was the square root of 4 minus x squared. It was a much better way to do it. A regular substitution would have worked here. So yes, you could get through a trig sub. This problem wasn't that complicated. So, I mean, if you're very quick with it, it wouldn't have cost you too much more time. But a regular u substitution was actually the better option here. Let's look at the other example.
I just have a quick question
Yes.
about that one. What happened to the -2 that was a part of the original answer for the integral?
It canceled. This -2 here,
Yeah.
it got canceled with the half
Oh,
right here.
oh.
And here's the last example. This is way for now. All right, what about this one? What did you guys do here?
I did u squared equals x squared minus 3.
How did you apply that here?
Well, then I differentiated both sides, so I got 2u du equals 2x dx, and then u du equals x dx.
Yeah.
Then I rewrote the numerator as x squared times x, and then ended up replacing the whole numerator with u squared plus 3, and then the denominator with u.
Right, so this guy here is your u du. This guy here is just u. And this guy here is going to be your u squared plus 3. And so this just becomes u squared plus 3. So that's u cubed over 3 plus 3u plus c. And so now you would get x squared minus 3 to the 3 over 2 plus 3 times the square root of x squared minus 3. So yeah, regular substitution works there. And not too bad, very quick. Which leads to this last the last question. To trig sub or not to trig sub? That is the question. So the last two examples kind of indicated that there are times when not doing the trig sub is actually better for you. Did you guys figure out what the deciding factor was? Can you guys like give me a rule? When would you use trig sub versus not use trig sub?
So maybe would you not use trig sub if there was an x in the numerator?
Here we had an x cubed in the numerator.
Like I think like any factor of x. Because it seems like with the 1 in the numerator, we were able to do trig sub, and then the 2 with x's in the numerator was easier to do. Like not easy.
Okay, so you're saying you do a u sub here?
Generally,
Trig is better here.
don't you do u sub if the power in the denominator is 1 greater than in the numerator? That was my Calc 1 teacher's go-to rule.
Power in the denominator is 1 greater than the numerator?
Yeah, the absolute value of it. So if you have say like x over x squared.
No, that's not really a go-to rule, because if I had something like this, that's also a u sub, and it's not 1 greater. Not this. Right, so the denominator has a 4 powers higher than the...
Well, technically no, because it would be 6 times 1/2, so it'd be 3, so it would be 1 higher.
Right, but that's after you did the substitution though, right? Like after you did something like, so here what you would do is like a u equals x cubed. So your du would be the 3x squared. And so this guy would be 1/3 1 over the radical of 1 minus u squared. Right, so I mean, visually speaking, if I just looked at that problem, the power in the denominator is actually 4 points higher.
I have an idea.
Yeah.
So in terms of the factors of x, if the denominator's factor is equal to the numerators after you take the square root of it and then differentiate it, then it would be easier to do a u substitution. Because like in the above example, the x cubed over 1 minus x to the 6th, if you took the square root of x to the 6th, then it would be x cubed. And if you differentiated it, it'd be x squared. So the substitution goes cleanly.
Yeah. What about this though? Something like that one. Trig sub or U sub?
You could still do a U sub.
Yeah. How do you know? Okay. Trig sub or U sub? Trig sub or U sub?
Does it have to do with the powers being even and odd?
Yes. Are you, so you, okay, so what is the rule? So for this one, the one on the right, the x to the 17th, what would you say?
Like because the numerator's power is odd and then the denominator's power is even, that would be, I think, U substitution? No, trig. Oh, no.
You're right the first
Dang
time. That's the U sub. This one is a trig sub. Like if you try to use a U sub on the one on the left, it would not work. This one, U sub, right? So yes, it has to do with even and odd powers. So let's actually write that down as a rule. How would you know, like for example, in these last two examples, when I gave you this example, the x cubed over blah, 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 and in this example, when I just gave you x over the blah, 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 why would you choose the regular substitution as opposed to the trig substitution? And it all comes down to the powers being even and odd. So if you have an odd power of the variable, as a factor, perhaps after a substitution. So that will cover the x to the 6 case that I mentioned earlier. Then a regular substitution would work. A regular substitution would also work if you had an odd factor in the denominator. But chances are you'd need another technique as well. Chances are you'd need an additional technique. So that's an example like something like x cubed over x squared plus 1. So something like that. If you have an odd power in the denominator as opposed to the numerator, you can still kind of get this to work. Chances are, though, you're going to need to tweak things a little bit. You'll probably need more than a substitution in most cases. The technique that you would need in this case, I'm actually going to teach you in the next section, so don't worry about that. But basically, that's what you're looking for, odd versus even powers. So if you have an even power of the variable, as a factor elsewhere, use trig sub. So that tells you here, if I'm doing trig sub versus, I hate calling it u sub, but trig sub versus u sub. If I see something like an x squared over the radical of a 1 minus x squared, that's a trig sub. If I see something like an x cubed over the radical of a 1 minus x squared, that's a u sub. And it does, even if the powers get larger, you don't have to worry about it. So if I had some like x to the 6 over the radical of 1 minus x squared, that's a trig sub. If I have something like x to the 7th over 1 minus x squared, that's a u sub. So you can actually determine which would be better, which you would get to work out based on the factor that's left over after you do the substitution. So the trig sub or the u sub is going to get rid of that x squared. So I look, okay, after I get rid of that x squared, what factor am I going to be left over with? And here you see there's an even factor and there's an odd factor. Here, whenever you have an odd factor of x left over, regular substitution would work. So that's what these last two examples were meant to show you. So not just go into a trig sub as a knee-jerk reaction. One thing you want to notice about trig sub is it tends to be more computationally intensive. So one of the reasons for that is it has this whole back substitution component. There's a whole process you have to go through to do the back substitution. In addition to, you're converting to trig integrals, you'd have to do it as a trig integral, then do a back substitution. Just going to a u sub first, chances are the substitution, the regular substitution is going to be easier computationally speaking. So you don't want to do a trig sub when you don't have to. And one way that you can visually kind of see, the powers don't have to differ by 1 or anything like that. The difference in the powers can be huge. It's just whether or not you have an odd versus even. And I put in parenthetical statement here. This might happen after you actually do a substitution. So yeah. Okay, and I think that is all we have for time. So I wanted to at least introduce the next topic, but we won't have time for that today. The next topic is going to be partial fractions, integration by partial fractions. It would be good if you can actually kind of read ahead on that. For next time, because of course you want to get a head start on the quiz. But for today, we're going to stop right there. And I believe okay. Yeah, so we're going to stop right there. I have an office hour meeting right after this, but that's it for today. So let us, yeah, move on. Hopefully you guys followed along okay. Thank you for attending. Thank you for your participation. Yeah, read ahead on partial fractions if you can, and we will stop there. So good night, everyone.
Thank you.
Thank you.
All right, take
Thank
care.
you,
See you
Professor.
guys in the next one. Ciao.